Good morning, students. Welcome back to finite element classes. And today is class 6 of module 3, and that is analysis of shafts. And in continuation, in the previous classes, we'll continue with the problems. Now, let us look into the new problem, that is problem number 2. Here, a bar of circular cross section having a diameter of 50 mm, which is firmly fixed at its end and subjected to a torque at point B and C as shown in figure. Determine the maximum angle of twist and shear stress in the material. Take rigidity modulus G as 7 into 10 raised 4 Newton per mm square, and Young's modulus is given as 2 into 10 raised 5 Newton per mm square. Now look into the sketch here. It is a uniform rod and which is having the total span length of 4 meters, and there is a two torques, that is 1 kilonewton meter torque is applied at a distance of 2 meters from the left end, and along with that one there is 1.5, that is a second node. At a third node there is a 5 kilonewton meter torque which is applied at a distance of 1 meter from the right end. Now for this problem we need to analyze by our regular FEA techniques. Now he has given the diameter. By considering the diameter, we will write the polar moment of inertia equation as J is equal to pi d to the power of 4 divided by 32. And since the diameter is 50 mm, we will take it as 50 mm, that is pi 50 to the power of 4 divided by 32. And so we will get the polar moment of inertia as 6.1359 into 10 raised 5 mm to the power of 4. This is the polar moment of inertia for the rod. Now we will go for the step 1, that is convert the physical model to finite element model. Now to convert this is a bar and it has been divided into 3 parts. So we will be considering it as a 3 elements, that is element 1, element 2 and element 3. The element length of element 1 is 2 meter, second element is having element length of 1 meter, and third element is having an elemental length of 1 meter. And torque T1 and theta 1 is applied. T1 is applied at node 1 and T2 is applied at node 2 and T3 is applied at node 3, and similarly T4 is applied at node 4. Now this is the first step for to convert the physical model to finite element model. Second step is the element stiffness matrix for the rod element. For the rod element, the element stiffness matrix can be written as K is equal to Gj divided by L into 1, minus 1, minus 1 and 1. Now where G is 7 into 10 raised 4 Newton per mm square and J, due to the diameter is 50 mm, we will take it as pi d to the power of 4 divided by 32, that is pi into 50 to the power of 4 divided by 32, that is 6.1359 into 10 raised 5 mm to the power of 4. This is the polar moment of inertia for the rod element. Now the element stiffness matrix, since the body is being divided into 3 elements, now we need to determine the individual element stiffness matrix for 3 elements. Now let us consider the stiffness matrix for the first element. For the first element, we have the stiffness matrix as K1 is equal to G1 J1 divided by L1 into 1 minus 1 minus 1 and 1, where G1 is 7 into 10 raised 4 divided by 7 into 10 raised 4 Newton per mm square, and the length of first element is 2000 mm, and polar moment of inertia is also pi d to the power of 4 divided by 32. Now substituting these values in the K1, that is element stiffness matrix equation, we have K1 is equal to 7 into 10 raised 4 into 6.135 into 10 raised 5 divided by the length as 2000 into 1 minus 1 minus 1 and 1, and that we can reduce. We will take the power, we will retain the power outside, that is 10 raised 6 into the matrix of 21.5 minus 21.5 minus 21.5 and 21.5. This is the element stiffness matrix for the first element. Similarly, the element stiffness matrix for the second element is K2, that we can write it as G2 J2 divided by L2 into 1 minus 1 minus 1 and 1. Since G is common for all the elements, we will take it as 7 into 10 raised 4 Newton per mm square, and length of the second element is 1000 mm. Now the polar moment of inertia also is same, that is pi d to the power of 4 divided by 32, that is 6.1359 into 10 raised 5 mm to the power of 4. Now substituting these values in the stiffness equation, we have K2 is equal to 7 into 10 raised 4 into 6.135 into 10 raised 5 divided by 1000 into 1 minus 1 minus 1 and 1. So in this equation, we will be retaining the power, that is 10 raised 6 outside, and only the values numerical will be sending in the bracket, that is 42.9 minus 42.9 and minus 42.9 42.9. This is the element stiffness matrix for second element. Similarly, the element stiffness matrix for the third element can be written as K3 is equal to G3 J3 divided by L3 into 1 minus 1 minus 1 and 1. Now since it is a same material, G remains same, that is G is equal to 7 into 10 raised 4 Newton per mm square, and length of the third element is 1000 mm, and rigidity modulus is also same because the diameter is uniform. Since the diameter is uniform, we have the same value of J, that is 6.1359 into 10 raised 5 mm to the power of 4. Substituting these values in element 3, that is element stiffness matrix equation, we have K3 is equal to 10 raised 6 42.9 minus 42.9 and 42.9 and 42.9. This is the element stiffness matrix for third element. Now we have determined the element stiffness matrix for element 1, element 2 and element 3. Now considering these three element stiffness matrix, we will be writing the global stiffness matrix. See, the global stiffness matrix is a combination of the element stiffness matrix. So that is K is equal to K1 plus K2 plus K3. Since we have combined the element stiffness matrix first, K1 plus K2, and we need to mention here K1, consider K1 because I have written only K1 and K2. Along with this one, you add up with K3. So on combining the element stiffness matrix, we have K is equal to 10 raised 6, 21.5 minus 21.5, 0, 0, minus 21.5, 64.4 minus 42.9, 0, 0, minus 42.9, 85.8 minus 42.9, 0, 0, minus 42.9 minus 42.9. This is the global stiffness matrix for the bar, or that is for a shaft element. Now the next step is the global load vector, and here the load vector is nothing but a torque. Since we have the 4 nodes, we will be having the torque vector as there is a load vector or torque vector. We can consider in spite of load, we are taking here torque. T is equal to the vector as T1, T2, T3 and T4. That is at node 1 T1, at node 2 T2, at node 3 T3 and at node 4 T4. And since there is no any load applied at node 1 and node 4, and since because there is no load at node 1, that is a torque, so we will consider it as 0, and there is a torque at node 2, that is 1 kilonewton meter, and at node 3 also 1 kilonewton meter, whereas at node 3 we have the 1.5 kilonewton meter torque, and there is no any torque at node 4, we will consider it as 0. This is the load vector. Step 4 is the load vector. Step 5 is the equilibrium equation. We can write the equilibrium equation as KQ is equal to T. And here the displacement is angular displacement. We will consider it as theta. So here we know already the global stiffness matrix and the global displacement vector and global force vector or torque vector. And the global stiffness matrix is, we can represent it as 10 raised 6, 21.5 minus 21.5, 0, 0, minus 21.5, 64.4 minus 42.9, 0, and 0 minus 42.9, 85.8 minus 42.9, 0, 0, minus 42.9 minus 42.9 into the angular displacement vector as theta 1, theta 2, theta 3 and theta 4. Similarly, the global torque vector can be written as 0, 1, 1.5 and 0. This is the step number 5, that is equilibrium equation. Shall move for the next step, that is step number 6, applying boundary condition. Since the left end node is been fixed, that we consider it as node 1. So wherever the node is fixed, there is no any deformation or there is no any angular rotation. The same condition is also applied for the either end, that is a right end node, that is node 4. There is also, it is completely constrained, there is no any angular rotation. And due to this boundary condition, we write theta 1 is equal to 0 and theta 4 is equal to 0. Considering these boundary conditions or applying these boundary conditions, we will write the same again, the equilibrium equations. And since node 1 is fixed, by applying the boundary condition, eliminate the first row and first column which is related to node 1. So we need to eliminate the first row and first column. Similarly, node 4 is also a constraint, that is completely fixed. There is no any deformation. So corresponding row is the fourth row and fourth column should be eliminated. And on applying these boundary conditions and applying the elimination method of boundary condition, the reduced form of equilibrium equation can be written as 10 raised 6 into 64.4 minus 42.9 minus 42.9 and 85.8 into the displacement vector as theta 2 theta 3 into is equal to the load vector as 1 and 1.5. And here, since there are two unknown displacements, we have, by solving the above two unknown equations, we can determine the unknown angular displacement theta is equal to 4.074 into 10 raised minus 8 radians, and at node 3 the angular displacement is equal to 3.785 into 10 raised minus 8 radians. Now along with this one, he has asked the stresses in the element. See, because the shaft is tending to, because of the application of torque, the shafts are subjected to shear stress. Then we need to determine what is the shear stress developed in individual element. There are three elements. For these three elements, we need to determine what is the stress developed in individual element. Now let us consider the first element, that is the shear stress developed in the first element is tau 1 is equal to gr1 divided by L1 into 1 minus 1 and 1 into theta 1 theta 2. And here the rigidity modulus for the first element is 7 into 10 raised 4, and the radius, the diameter is 50 mm. We can write the radius as 25 mm, and the length of the first element is 2000 mm into the matrix. We can write it as the first one, that is by 2 by 2 matrix. We can write it as 4.07 into 10 raised minus 8. And by solving this equation, we have the shear stress tau 1 is equal to 3.564 into 10 raised minus 5 Newton per mm square, or we can write it as 35.64 Newton per meter square. This is the shear stress for the first element. Similarly, shear stress for the second element can be written as shear stress tau 2 is equal to gr2 divided by L2 into minus 1 into theta 2 and theta 3. That is a vector displacement where R2 is the diameter of the shaft, and here also we can represent G and R, and length is 1000 mm. That is the length of the second element. Therefore the equation can be written as 7 into 10 raised 4 into 25 divided by 1000 into minus 4.074 into 10 raised minus 8 plus 3.785 into 10 raised minus 8. On solving the above equation, we have the shear stress developed in the element 2 is tau 2 is equal to minus 5.07 into 10 raised minus 6 Newton per mm square, or we can write it as minus 5.057 Newton per meter square. And this is the shear stress in the element 2. Similarly, the shear stress developed in the element 3 can be written as the equation tau 3 is equal to G capital R3 and L3 into minus 1, 1 into the matrix of theta 3 and theta 4. Here in this equation, we have the values of the radius as 25, length of the third element as 1000 mm, and we have calculated the displacement, angular displacement theta 3 as minus 3.785, and because of the boundary condition theta 4 is also 0. Now on calculating the above equation, we have the shear stress developed in the third element as tau 3 is equal to minus 6.623 into 10 raise minus 5 Newton per mm square, or in terms of meters means we can take it as minus 66.23 Newton per meter square. So this is the question he has asked to determine the angular displacements in the element. Along with this one, he has asked to determine the stresses developed in the elements. Hence, the problem is solved. Now we shall move for the next problem, that is problem number 3. Here, a composite step shaft as shown in figure consists of an aluminium section 50 mm in diameter and a steel section of 25 mm in diameter, and both the ends of the shafts are fixed. Determine the maximum stress, or is the maximum stress in the aluminium and steel shaft. Take G for a steel member, that is a rigidity modulus for steel as 84 GPa, and rigidity modulus for aluminium as 28 GPa. So look into the sketch here. This is a composite shaft, and the composite shaft is made up of, one is the aluminium shaft and the other one is the steel shaft, and the steel shaft is having the length of 300 mm and the aluminium shaft is having the length of 300 mm, and diameter of the steel shaft is 25 mm and the diameter of aluminium rod is 50 mm. Now the composite shaft is fixed at either ends, that is the ends is both the ends have been fixed. So considering this one, we need to solve the problem and to determine the deflections as well as the maximum stresses in the two bars, that is either the steel bar as well as the aluminium bar. Now for this bar, you can observe there is a torque of 200 Newton meter which is applied at a distance of 200 mm from the left. From the left, it has been applied a torque of 200 Newton meter, and this is the forcing vector. Because of this torque, what is the angular twist and what is the stresses in the member we need to determine. And let us look into the data. By considering the data he has given, we can write the polar moment of equation for the shaft, that is for the first shaft, that is for your aluminium shaft. We can take it as, for the diameter of 50 mm, then we can write the polar moment of inertia as J1 is equal to pi d1 to the power of 4 divided by 32, that is pi into 50 to the power of 4 divided by 32, that is equal to 613.59 into 10 raised 3 mm to the power of 4. Similarly, d1 is equal to d2, we have j1 is equal to j2, and for the shaft 2, that is a steel shaft, we can consider that is as j3, that is pi d3 to the power of 4 divided by 32 is equal to pi into 25 to the power of 4 divided by 32, and that is 38.34 into 10 raised 3 mm to the power of 4. This is the data which he has given. So here the first step is to convert the physical model to the finite element model. Now let us write the finite element model, which includes only nodes and elements, and here the total body is being divided into 3 elements. Element 1 is having a length of 200 mm, element 2 of 100 mm, and element 3 is of 300 mm length. And these 3 elements are having 4 nodes. And T1 and theta 1, T1 is the torque at node 1 and T2 at node 2, similarly T3 and T4 at node 3 and 4. And the torque is applied, that is a T2 at node 2 and T3 at node 3. This is your element, what you call as finite element model. Step 2, we need to represent the element stiffness matrix for the rod element. We have the element stiffness matrix for the rod element as K is equal to Gj divided by L into 1 minus 1 minus 1 and 1. And for the first element, we can write the element stiffness matrix as K1 is equal to G1 J1 divided by L1 into 1 minus 1 minus 1 and 1. And where the polar moment of inertia for the first element G1 is equal to 84 GPa, that is equal to, for the first element he has given as he has given as 28, not 84, take it as 28 into 10 raised 3 Newton per mm square, and the length of first element is 200 mm, and substituting these values in the first equation. See, G1 for the first element is the aluminum element, which is having the rigidity modulus as 28 into 10 raised 3 Newton per mm square. On substituting these values, that is 28 into 10 raised 3 into 613.59 into 10 raised 3 divided by L1 is 200 into 1 minus 1 minus 1 and 1. On solving the above equation, we have the element stiffness matrix for the first element as the 10 raised 6 into 85.9 minus 85.9 minus 85.9 and 85.9. And the next one is the stiffness matrix for the second element. Since the element 2 is also having the same diameter, we can write the equation for the element stiffness matrix K2 is equal to G2, J2 and L2 into 1 minus 1 minus 1 and 1, where G2 is 28 into 10 raised 3 Newton per mm square and L2 is 100 mm. Now we can represent the values of, since element 1 and element 2 is of same material, rigidity modulus is also same, that is 28 into 10 raised 3 into 613.59 into 10 raised 3 divided by 100 into 1 minus 1 and 1. And solving the above equation, we have the element stiffness matrix for element 2 as 10 raised 6 into 171.8 minus 171.8 and minus 171.8 and 171.8. This is the stiffness matrix for element 2. Similarly, we have the stiffness matrix for element 3, and that can be written as K3 is equal to G3 J3 divided by L3 into 1 minus 1 and 1, where G3 is 84 into 10 raised 3, that is 84 GPa as well, converted to Newton per mm square, that is 84 into 10 raised 3 Newton per mm square, and length of third element is 300 mm. And substituting these values in the above equation, we have K3 is equal to 84 into 10 raised 3 into 38.3 into 10 raised 3 divided by 300 into 1 minus 1 minus 1 and 1. On solving the above equation, we have the element stiffness matrix K3 is equal to 10 raised 6 into 10.74 minus 10.74 minus 10.74 and 10.74. So we have found out the element stiffness matrix for the three elements. Considering this element stiffness matrix, we'll write step number 3 as global stiffness matrix. The global stiffness matrix is also, here we can call it as a summation of all the element stiffness matrix. That is, K is equal to K1 plus K2 plus K3. And here, on combining all the element stiffness matrix, we can write the global stiffness matrix as K is equal to 10 raised 6 into 85.9 minus 85.900 minus 85.9 257.7 minus 171.800 minus 171.8 182.54 minus 10.74 00 minus 10.74 and 10.74. This is the global stiffness matrix for the rod element. And next one is the load vector. Since we have applied a torque, we can consider it as the torque matrix as T1, T2, T3 and T4 at 4 nodes. And these values are, since we have not applied any torque at node 1, then T1 is 0, and there is no any torque at node 2, T2 is 0, and we have applied a torque of 2 kilonewton at node 3, that is 2, and at node 2 we have applied, and there is no any torque at node 3 and there is no any torque at node 4. So we will be considering it as T3 as 0 and T4 as 0. Now the step 5 is the equilibrium equation. We know the equilibrium equation, that is K into Q is equal to T, where K is the global stiffness matrix and Q is the global displacement vector, and matrix T is the global load vector or torque vector. Considering this one, we can write the equilibrium equation as KQ is equal to T. This is the equilibrium equation for the rod element. Now for this equilibrium equation, we need to apply the sixth step, that is applying boundary condition. Since the rod is being fixed at both ends, that is node 1 is fixed and node 4 is fixed, and since node 1 is fixed, there is no any displacements, so theta 1 is equal to 0, and since there is node 4 is fixed, there also there is no any angular displacement, so we will take it as theta 4 is equal to 0. Now applying the elimination method of boundary condition, that is we need to eliminate the corresponding row and column of the node whichever it is fixed. Since node 1 is fixed, its corresponding row and its corresponding column is eliminated. And the second boundary condition is node 4 is being fixed, and so we will apply the boundary condition is its corresponding row and its corresponding column should be eliminated. This is the boundary conditions we are applying for the equilibrium equation. Now after applying the boundary conditions, the reduced form equation can be written as 10 raised 6 into 257.7 minus 171.8 and minus 171.8 and 182.54 into the vector of displacement vector of theta 2 and theta 3 is equal to the torque vector as 0.2 and 0. In this matrix we have the two unknowns, that is theta 2 and theta 3, and for two unknowns, by solving the above two simultaneous equation, we have the displacements at node 2 as theta 2 is equal to 2.083 into 10 raised minus 9 radians, and similarly theta 3 is equal to 1.961 into 10 raise minus 9 radians. These are the two unknown angular displacements we have got. Now, considering these two angular displacement equations, we need to determine what is the stresses developed in the elements. That is shear stress. Because of the torque, there is a torsional shear stress developed in the member. This torsional shear stress we need to determine. Let us consider the first element. For the first element, we can write this shear stress equation as G1 R1 divided by L1 into minus 1 into theta 1 and theta 2. For this one, we will be substituting the shear stress values, that is rigidity modulus as 22 into 28 into 10 raised 3 and the radius R1 as 25 and length L1 as 200 into the displacement theta 1 is 0 and theta 2 as 2.083 into 10 raised minus 9. By solving the above equation, we have the torsional shear stress for the first element as 7.29 into 10 raised minus 6 Newton per mm square, and for the second we can represent in terms of meters as 7.29 Newton per meter square. Similarly, shear stress for the element 2 can be written as tau 2 is equal to G2 R2 divided by L2 into matrix of 1 minus 1 1 into the vector of displacement vector as theta 2 and theta 3, and substituting the values of G2 as 28 into 10 raised 3 into R2 as 25 divided by 100, that is the length L2 as 100 into, we can after multiplying the displacement vector as minus 2.083 into 10 raised minus 9 plus 1.961 into 10 raised minus 9. On solving the above equation, we have the shear stress for the second element as minus 854 Newton per mm square, or we can write it as minus 0.000854 Newton per meter square. This is the shear stress in the element 2. Similarly, the shear stress in element 2 in element 3 also can be represented as tau 3 is equal to G3 R3 divided by L3 into minus 1 into theta 3 and theta 4. Since there is no any angular displacement at node 4, theta 4 can be taken as 0 and G3 as 84 into 10 raised 3 and R3 as 12.5, that is radius is 12.5 and the length of third element is 300 mm. On solving the above equation, we have the shear stress for the third element as tau 3 is equal to 6.86 into 10 raised minus 6 Newton per mm square, or we can represent it as 6.86 Newton per meter square. This is in the question he was asked to determine the displacements as well as shear stress. Finally, we have determined the shear stress in element 1, element 2 and element 3. This is the problem. And here, by this, we will be winding up with this module 3, that is the analysis of beams and shafts. And by this, the model has been completed, and the next model 4 will be continued by our other professors, that is either Shuram sir or by Vijay Kumar sir. Thank you, all the best.